Physics Blender. I love 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 Physics Blender. Subscribe for more videos.
Hello everyone, welcome to Physics Blender e-learning platform. Today we are discussing sound waves. We are discussing paper 4 classwork. This paper for extended candidates only. We have question 5 asking you to describe how the cone in the figure is producing sound waves, and the frequency here is given. And you have here a hollow paper cone. Okay, the first point, this is connected to an alternating current, and or you will know in electricity that we have two types of currents. We have direct current and AC, which is alternating current. The alternating current in the coil makes the paper cone to vibrate in and out, and this happens 50 times per second. According to the country, the frequency of the generator could be 50 times frequency 50 hertz, which means the direction of this current, or the current is alternating 50 times per second. So what will happen to the air particles here, which are close to the paper cone? Also, they will produce compressions and rarefactions, and these vibrations will be along or parallel to the direction of energy transfer. Is it clear? So you have to mention all these points. You have a question, 3 marks, so you have to mention all the points in details. Let's write down the answer now. So the alternating current in the coil makes the paper cone to vibrate in and out. So what happens? The neighboring air particles vibrate producing compressions and rarefactions. Okay, these vibrations will be parallel or along the direction of energy transfer or direction of wave travel. Is it clear? It's very important question, and it's very simple. I should tell you that according to the source, or according to the country, the alternating current depends on the generator according to the country. Sometimes we have frequency. You will see the device labeled 50 hertz or 60 hertz. It differs according to the country. The second part, the speed of sound in air is 330 meter per second, and this value should be known. You know this value already. Calculate the wavelength of this sound. According to wave equation, speed of sound is equal to wavelength times frequency. And again, guys, this triangle will not be accepted. You can use it just to revise, or you can remember the equation, but this equation should be written as an equation like this. Okay. When you substitute here, you are trying to find the wavelength, which is equal to speed of sound in air divided by frequency. Check units are consistent. So you have 330 meter per second. Check the frequency is hertz, not kilohertz, not megahertz. So the frequency is given 15,000 hertz. The answer is 0.022 meters. So this is the answer. You have to write it here. The unit should be mentioned. The last part of the question is asking you here to sketch a diagram that represents sound waves in form of wave fronts. We have here a barrier, and this barrier, it has a gap. The width of the gap is double the wavelength of sound. So if waves are traveling in this direction, how you can draw wave fronts? Let's draw wave fronts. Okay. The width of the gap is almost 3 centimeters according to my diagram. So you have to draw wave fronts. The distance or the spaces between wave fronts will be almost 1.5, half. So the wavelength here almost 1.5 centimeters according to my diagram. So we will draw here 2 or 3 wave fronts. So we are sketching, no need to measure. Okay. What will happen when they enter the gap? The wavelength will not change, will be the same, but we will show diffraction, but the diffraction will be only slight bending at the edge. Okay, like here. Slight bending at the edge. So if you have here the direction of wave travel, the direction of wave travel will be in this direction. Make sure that wave fronts are at right angle to the direction of wave travel. What happens here? Slight bending at the edge, change in direction, and here we have change in direction. Let's revise what happens in diffraction. The wavelength will be the same. Wavelength will be the same. Okay, no change in wavelength. Frequency will be the same, speed will be the same, only change in direction. So change in direction but slight bending at the edge, not circular wavefronts. We have circular wavefronts if the dimensions of the gap is equal to or less than the wavelength of the wave. Okay, or approximately. We have significant, we have clear diffraction if you have the dimensions of the gap is almost equal to the wavelength of the wave. Okay.
Subscribe for more videos. I love physics splendor. I love physics splendor. I love physics splendor. I love physics splendor. I love physics splendor.